Where is the switch?
Yeah, that's right. So we can operate. Here's the switch. Should I switch it? Did something go bad? I think it's the microphone switch. I think it's behind.
We should get started.
Yeah.
Hello everyone. My name is Mausam. I am from IIT Delhi, and it's my honor to introduce Professor Qiang as the invited speaker for the evening. Although for most AI audience, Qiang should need no introduction. Qiang is a chair professor and head of Department of Computer Science and Engineering at the Hong Kong University of Science and Technology. In his illustrious research career, spanning just over 3 decades so far, Qiang has already written over 400 peer-reviewed papers at top AI and data science venues. I would say his AI research spans almost all subfields of AI. With such an accomplished publication profile, it is no surprise that Qiang has received numerous accolades, such as being a AAAI Fellow, an AAAS Fellow, an IEEE Fellow, the International Association for Pattern Recognition IAPR Fellow, and more recently, an ACM Fellow. He has also made numerous service contributions to these fields, including starting 2 journals, ACM Transactions on Intelligent Systems and IEEE Transactions on Big Data, serving as a PC chair for HKUST 2015 and KDD 2010, and chairs for many other conferences like ACM Rexis, IEEE Big Data, IUI, and ICCBR. He is current president of HKUST and a AAAI Executive Council member. For his numerous contributions, he was honored with the ACM SICK KDD Distinguished Service Award in 2017. Qiang has also co-authored several books, including a valuable resource to young researchers on how to complete a successful master's and PhD degree in science and engineering. That book is on display outside at the Morgan and Claypool booth. Before moving back to Hong Kong in 2001, Qiang spent several years in North America, first completing his PhD at University of Maryland in 1989, and then as a faculty member at universities of Waterloo and Simon Fraser. It is, however, lesser known that Qiang has an undergraduate and a first master's degree in astrophysics. I think we will all agree that what has been a loss for astrophysics has entirely been a gain for the field of artificial intelligence. Please join me in welcoming Professor Qiang.
Thank you. It's really an honor to give an invited talk at AAAI. So let me get started. My title is GDPR, Data Shortage and AI. So when reading the title, you may be wondering, what am I going to talk about? Let's start. So I will start by telling what everybody already knows, that data is critical for AI's achievement today, right? No matter what algorithm you are using, the more data you have, the better performance. So for example, as the chart on the left shows, this is ImageNet result up to 2016. And as you can see, the error rate decreases dramatically as the year progresses. And what is not shown here is as the years getting close to now, the amount of data used in training also astronomically increases. On the right is a chart from a recent work in Google, which further underlines this point that pre-training with a large amount of data will dramatically increase the performance. And so AI and big data go hand in hand. On the other hand, when we look around each one of us, we notice only small data, especially for people at the university, and also for many people in small and medium-sized companies. Here I only quote a few evidence. So for example, there's a law firm that reported that typically they have contract as data samples for contract review models, but they experience between 10,000 and 20,000 of those samples, and getting more is very, very difficult. In the finance industry, one deals with very large loans. Usually, so for example, in the car loan industry, when dealing with expensive cars, successful samples are very rare, very few. And in one case, in the Ford paradigm, a startup in China, they only have close to 100 examples as typical examples. So building a credit rating model is exceedingly difficult with so few data. In medical image, I'm sure many people around are interested or already doing research there, and getting data is also a challenge. Many such examples show that. Now, on top of this, as we know, data is entering the mass media, and our society is increasingly concerned over all aspects of data, especially confidentiality and privacy. And on top of this, regulators and governments are placing more and more constraints to limit the use of data and to, in order to protect the privacy. So many news. And so in conclusion, what we expect today is big data, lots of data, and we expect to have sufficient data to train our models. And there's some people even say that we live in an era of big data. But here I would like to refute that. Instead, I believe that the era we live in is the era in which we only have fragmented data and small data. And big data are only in the hands of extremely few companies. So what do we do? So this poses two challenges for AI. Most people only have small data. How do we train our models? How do we build successful AI applications? Another issue is fragmented data. When data are scattered but cannot be easily fused and integrated together, what shall we do with this data? And here, in this talk, I will give two solutions which are part of my research. The first one is transfer learning, which migrates or transfers data and knowledge from what we know before to unknown and new domains. And in this area, we can think of two words, big and small. Big is something we have already built up, something we have experience with, a model which is reliable. And small is something new, and we want to transfer from big to small. Another one is fragmented data, and here I want to introduce to you a new idea, a new development. It's called federated learning. And many people are already paying attention, but I think it's beneficial for more people to know about this area and perhaps to join in this research. So let me start from transfer learning. So transfer learning is motivated by the human ability to easily adapt our abilities from one area to another. So for example, when we learn how to ride a bicycle, we find it's very easy to learn something similar like a motorcycle without much effort, right? So this is an example of, when we took a lot of trial and error and failure and success to train a bicycle model, and then we can easily transfer that experience to benefit the experience of motorcycle. So to put it in machine learning scenario, Here in blue, we have a domain we call source domain, where we have some well-labeled data, we have a well-trained model, and we have some tasks where the performance is high. In the red color, we have some new domains where we only have small data, and they are called target data. And the model is not there yet, okay? So we try to build the model with a small amount of data, and maybe the task is also new. It's different from the source domain. And so the source is where the knowledge comes from, and the target is where we are interested in. Okay, so this is the scenario. And if we can do transfer learning, there are several benefits in terms of computer science and AI perspective. I already said that one challenge we try to tackle is the small data problem. So if we have only small data, given that we have a successful model that's sufficiently similar and relevant, we can do this transfer, and therefore we can build a model successfully even though we have small data. But another thing which machine learning people currently are increasingly interested in is the reliability of machine learning models. So if you build one model, now if we extend the boundary of this model and task, how do we benefit something similar, something maybe very different, something maybe even heterogeneous in nature, in features, and so on. So the reliability and robustness of a model can benefit from the result of transfer learning. And yet another one is personalization. Suppose we have a general model which is trained to benefit everybody. Now we want to personalize and individualize that, maybe on a client. Now how do we do this transfer from a general model to an individual model? And for each one of these advantages, I'm going to give you examples of our research in this area. And yet another important area is not only shall we be able to do transfer, but we should be able to learn how to transfer. And research issues involve endowing machines with the ability to figure out when to do the transfer, how to do the transfer, what to transfer and what not to transfer, and learning how to learn. Okay, so learning how to learn is really the heart of the ability to transfer. Now, but when we start this research, actually I'm thinking, how does it benefit our everyday life? And here's one example. Because I work in Hong Kong, I travel sometimes to mainland China across the border. And the driving is different. In Hong Kong, they follow the British style, where the driver sits on the right-hand side of the car. When we switch to mainland China, it's like here. The driver sits on the left-hand side of the car. How do you do this switch in 1 second? And finally, I figured out the solution lies in transfer learning. The key is to find what is invariant between these two domains. That is the distance between the driver and the center of the road. That distance is minimal. Okay? So as long as you remember this, you can do this transfer without any risk or danger, and I encourage everybody to try it. Okay, so put it in computer science term, how does this work? Now, a recent work on deep learning and transfer learning integrated together give us some very good examples. So if we take this top stacks as a deep learning model, the lower level correspond to the left-hand side, and the top layer correspond to the right-hand side. Then we can see that we can partition the learning task into individual layers. Shall we transfer something closer to the lower layer from top down? Shall we transfer something in the middle, or something to the right? Right. So this is really this really corresponds to what to transfer question. Okay. And so remember that driving example. It tells us to find what is common between the two domains, what is not easily changed. And so depending on the task at hand, we can decide which part of this model we can do the transfer. And so in a recent work by Yosinski et al. In 2014 NIPS, a very scientific work is given on studying the transferability that corresponds to different models in a deep learning model. And so here, the horizontal axis shows the layers, 1 being the bottom layer and 7 being the top layer. And the vertical axis corresponds to the performance. As we can see, if we just do the performance evaluation layer by layer, and here each point is the result of a collection of experiments, we can see that generally the lower layers perform better for transferring. In other words, closer to the bottom gives us more common knowledge, which we can use for transfer. And this is for image data. But maybe for audio data, the scenario is different, okay? I'm still waiting to see work in that area. So here is a very good direction for graduate students. Try it for different type of data and study the transferability of different layers in a deep learning model. So this gives us a good idea of how much to transfer, what to transfer. And so when we partition the research work into even finer details, we can separate them into different scenarios. The first scenario is known as unsupervised transfer, where we have sufficient label data in the source domain, label or unlabeled data. But in the target domain, we have completely no label. Okay, so here we just look at the behavior of the data itself, not the label and the task, and figure out the distance between them, and therefore figure out what is common between them. And in natural language processing, this problem is known as domain adaptation. Okay, just looking at the data and figure out what to transfer. Another setting is we have label data on both sides, and we can do more in that case. So let's look at each case in turn. And here I want to, so there are many examples in the first setting, and here I just want to give you a example through a group, a work from my research group, and this is primarily done by my graduate student, Zheng Li, who also has a paper here at AAAI. And the work is on sentiment analysis from natural language comments. Okay, so the task here is given many comments, some positive, some negative, on products like on Amazon or online shopping. Figure out the orientation, like a thumbs up or thumbs down for these comments just by analyzing the natural language text. We know that this is very useful, and it's also labor intensive to label this data to figure out which part corresponds to positive or negative sentiment. So in one domain, if we want to build a good model, we have to do enough labeling. But in transfer learning, we are more interested in cross-domain setting. Okay, so how do we cross from one domain where we already have labeled data to a new domain where we don't have labeled data? So this work, because of its importance, has been visited by many researchers in the past. So about 15 years ago, people have looked at from a point of view of exactly figuring out what is common between the two domains. And in this case, those words that are both sentiment sensitive and common between the two domains are known as pivots. And in this work by Blizzard and al., they allow humans to figure out what the pivots are and then use them as a bridge to transfer. Okay, so for example, once we mask some of the pivots, we can generate a lot of natural language text tasks as classification tasks. And once these tasks are performed, we can figure out how these pivots can allow the sentiments to be transferred, which allow us to compress and to take the samples from 2 domains and unify them. Another work is by Sino Pan et al., also my student, who took the idea but took a different approach in order to figure out what's common between the 2 domains. And here they use spectral clustering to find out what might be pivots, okay? But both of these works rely a lot on human labeling, initial labeling of the pivots. So in fact, this further work by my graduate student, Zheng Li, took an adversarial learning approach, which can not only figure out a model in the new domain, in the target domain, but also automatically figure out the pivots. And how it's done is like this. As we can see, there are 2 deep models, one on the left, one on the right. The one on the left, because we have lots of label data in the source domain, the one on the left tries to minimize the error, classification error in the source domain in order to build this model, so optimizing for the performance. But the one on the right tries to maximize the domain difference, maximize the domain classifier error, well, which tries to minimize the domain difference. Okay? When you cannot tell the difference between the 2 domains by only looking at the pivots, then these are good pivots. Okay, so we want to find out those bridge words which can not only give you a good sense of sentiment, but also can be ambiguous in telling which domain they are from. And when both goals are optimized, we can find the good pivots, okay, such as those which are marked as blue. And the red bar here shows the performance of this work. Okay, so this is an example of when we have lots of label data in the source domain and no label data in the target domain, and we can figure out a bridge between them. To take another example in the setting 2, which is when we have some label data in the target domain, we can take a dialogue system, something also from natural language. In building a dialogue system, we know that the dialogue transactions are very important as training data. And here we took the task of task-oriented dialogue system, which have a final goal to achieve. So it's not just free chatting, but also, but instead it is for satisfying some goals, such as satisfying the customer service or online shopping and so on. So on the left-hand side, we have a sufficient number of transactions. Each is labeled with success and failure. Okay, they are multi-turn dialogues. And now our goal is to find something which allow us to do transferring to a individualized or personalized dialogue system, which dialogue can be much shorter than a general dialogue. For example, when you ask somebody what kind of coffee would you like in Starbucks, if you don't know anything about this customer, you will ask from the beginning, what type of coffee, do you want milk, do you want hot or cold, and so on. But if you know something or quite a lot about this customer, then you can go directly to the target. Would you like the same thing as last time? So the conversation can be much more efficient. Okay, so the benefit is very clear, but how do we do this? The idea is to combine transfer learning with reinforcement learning. And here we can partition the Q function into 2 parts. One is the general Q function, which governs the conversation process and policy for everybody. Another one is a personalized Q function which controls the same thing but more personalized for this individual's preference. And in the heart of this transition is very, very critical to find the right representation for belief state. Where do you think the conversation has progressed to? What should the next action be in terms of the speech act? And so when we can figure out a good belief state representation, a vector representation, we can use that to train this personalized Q function. The result is actually very good. Okay, so not only it can perform the task of a slot filling for transferring between users. So for example, here is a transfer between one person who asked about a hot latte to somebody who's interested in mocha. But the dialogue is in similar style, but also across domains, from somebody interested in coffee to finding a hotel. And also it makes the whole conversation on average much shorter. Okay, so here is a few experimental results which we use real data collected from a O2O company in China for filling the customer orders for coffee, taxis, and a variety of things. And the result is dramatic improvement and improvement in user experience as well. Okay, and yet another application of transfer learning in reinforcement learning is in the mobile news recommendation area. In this area, as we know, so on the right-hand side is an example of a mobile display, news display page. Okay, so in this area, when you have lots of news to recommend to an individual user, you have to be careful to balance between exploitation and exploration. And this is a very classic problem in reinforcement learning, right? Now, if you are only have exploitation, then you will go into a local minimum and the user only read about what they have read before and get nothing else. And that's very bad experience. But if you only have exploration, then the user will only read random news, and that's not good either. Okay, so this balance represents how smart the system is. Now, suppose in one domain we have strike a right balance between exploration and exploitation, this policy. Now, when we want to transfer to another domain, say a technical domain to a general news domain or something like that, we have to recollect the data and relearn. But using transfer learning, we can avoid this so-called cold start problem by figuring out what's common between the two domains and allow this transfer. So in terms of the actual policy, we use this model known as contextual bandit, and then added a transfer learning component to it. It's called transferable contextual bandit, which generated very good performance and was put to actual use in several large-scale news recommendation domains. Okay. More recently, so far, all this work have been requiring a lot of human engineering, a lot of ingenious design. And so we ask, are there any general processes, almost like a software engineering model, which can guide us through a transfer learning process? And recently, I've seen two works which gave a very good pointer in this direction, and I'm quite excited to see it. And this is to use a huge pre-trained model, maybe a general model, but using lots of data. As you can see, the source is much larger than the target. And so the larger the source, the smaller the need for the target. And so you only use a few examples to do fine-tuning. And this model has been used a lot in image, in computer vision area, as well as recently in natural language processing area. So in the computer vision area, recent work by Mahajan et al. Titled "Exploring the Limits of Weakly Supervised Learning," pre-training really put this to spotlight. So they have increased based on the traditional ImageNet data set, which has 10 to the 7th image, dramatically to 10 to the 9th power. And this curve shows the performance of transfer learning with a few labeled examples in the target domain. And as you can see, the performance is close to getting sufficient data in the target domain and training from the beginning. So this is very, very encouraging. And it may mean that in the future, when we want to do transfer, we must start with a powerful pre-trained model, and then we look for related new domains. In another well-known work, this work came from Google by Devlin et al., and it's a well-known BERT system, which used a pre-trained language model to adapt to a variety of different natural language processing tasks and achieved success. So this really gave us some hope that transfer learning has come to age, and maybe it will affect the practice of machine learning in the future as well. At the beginning, I mentioned that it's not only important to learn algorithms that can perform transfer learning, but also to model the human ability to continuously adapt. Okay, so transfer learning via learning to transfer is a recent ICML paper my students and I composed. So the idea is horizontal axis is the experience a person may experience in a lifetime. And so sometimes you see images, sometimes you see natural language, you read, sometimes you engage in some professional activity such as satellite imagery of weather and medical image. So when you go through this, they actually, each task can benefit from all the previous experience. And so in fact, they can mutually influence each other. When you even go back to some task you visited before, you can see the benefit. And so how do we do this is we compose pairs of training data from a source to a target. Every time we perform a transfer learning successfully, we can take that experience and compress it into what we know as what we call transfer component. And when we collect enough of these components, we can perform some eigenvector analysis as shown on the right-hand side in a hypergraph. And then when we meet with a new problem, we can then fit that problem and compose a solution based on those transfer components, which gives us suggestion on the best transfer learning algorithm to use for this new problem. Okay, and in our limited experiments, the result is good, and we wish to further extend this. So this work is also very related to lifelong learning, which many people are interested in. So to summarize, transfer learning from large data to small data, from old data to new data, and to make this process continuously along the timeline is our interest, and I believe this area will take machine learning to a new level. Next, in the remaining time, I wish to focus on the second problem, which is what do we do when data are fragmented. When we look at this, we cannot ignore the issue of data privacy and confidentiality, and here are two of the news which everybody must have read about data leakage and so on, and regulation on these events. A recent event, I'm sure many people have heard, is that Europe enacted a law on data privacy and confidentiality known as the General Data Protection Regulation, GDPR. A few items related to machine learning and AI include the following, right? So autonomous modeling and decision have to be very controlled and have to be have to be assigned to people responsible. Interpretability is raised to a legal level. Users' right is utmost. Okay, users even have the right to ask for their data to be forgotten, and so on. So this places a very strict limit on companies who must share data in order to build a bigger model. So that's why it is relevant to the topic in this talk. So in fact, the way we look at GDPR, we shouldn't look at it negatively. Our view is that GDPR is really in the right direction for the humankind and human society. And as AI researchers, we should take this challenge and build our system which can be compliant with laws like GDPR. In fact, not only in Europe, but also in close to here, the California law is about to be enacted in 2020, which have some items very similar to GDPR. And also in China, the law is also very strict and have been applied to a few cases which made headlines. And in particular, it forbids people to illegally trade data on the market and for companies to exchange data without user consent and permission. So with all these coming up and with the current fragmentation of data, we are at a loss, right? So on one hand, our data is in fragmented format. So here on the right-hand side is an example. In maybe some enterprise A only has some user behavior data that it has collected as part of the service. On the right-hand side, we have an enterprise B, which has some behavior data along with some label data, although labeling the data may be expensive and laborious, and so it's not sufficient to build a good model. So traditionally, when these two companies come together, they will just strike a deal without considering law and people's privacy. But now, they cannot do that anymore, okay? So the question is, how do we combine the knowledge in this data without violating user privacy and confidentiality? Is it possible to do? Okay. Now, in fact, when we visit the techniques at hand, we do have people who have studied this issue for years, maybe not from AI perspective, but from general computer science perspective. So for example, there's this technology known as secure multi-party computation, or MPC. Another is called homomorphic encryption, which we use in subsequent work. There's Yao's garbled circuit, which is well known, and Andrew Yao got a Turing Award because of this contribution. There's a technique called secret sharing and a well-known technique known as differential privacy. So people have paid attention, although none of these came from AI. So the question is, can we exploit some of these in building our AI models, especially given the data fragmentation problem? So when we look at secure the MPC approach, it has many advantages, but it does require a coordinator to exist, and everybody has to trust that coordinator. Not only is this process suspicious, especially given the coordinator can turn against the interested parties in data leakage, but also the process is very, very expensive computationally, right? So, so there is a work, there are examples of works which integrate this MPC with maybe logistic regression, linear regression, and so on. But the efficiency of this work still calls into question. But these are good directions to go. Gauss-Garbo circuit allows two parties, here in the example is Alice and Bob, to build models, use each other's data without sharing the actual, the private information. And this is done theoretically very well, but it's very expensive. Recently, in the encryption area, homomorphic encryption allows people to take the encryption itself and distribute them into each terms in a polynomial, as we can see from the addition and scalar multiplication. So the implication of this is great for machine learning because it means it's possible now to build a model without knowing what the data has, okay, what the content of the data. You can have a model building algorithm which controls, which builds the architecture and the model, a sophisticated model, but the elements you are working on, you don't have to know the content. So we will see an example of this. In particular, we can expand this, all the functions needed in major machine learning algorithms such as deep neural net and logistic regression, and distribute this encryption term into each element. Okay, and this can be done efficiently. Now, this allows us to do one thing, is to let two parties share the gradient in encrypted form. But if two parties share enough of the ingredients in pieces, eventually it's still possible for them to figure out the data, as shown by the circle here, right? So from left to right, the right-hand side photo is a reconstruction based on the shared encrypted gradients. So this tells us that when we build a secure machine learning model, we must come up with a security model as well to show that no attacks can rebuild the data, can reverse engineer the data. And we have a recent survey paper on ACM TIST journal that addresses this issue. And when we look at federated learning in more detail, we can see we can further partition it into two directions. So when we consider data roughly as a matrix, where the vertical axis are, so each row corresponds to the data of one user. Okay, so the horizontal axis are users or samples, and vertically we have features. Okay, so for example, pixels or user information. Then this matrix roughly tells us a data model. If we partition the data between different parties along the user dimension, this is known as horizontal partitioning. If we partition based on features, so one party has some features, another party has some other features, this is known as vertical partition. So we can look at each one of these separately. In the horizontal partition is the division by users. There are well-known algorithms that people are studying currently. Okay, so the steps corresponds to masking the local model, masking their gradients, and send the masked result to a central server. And the central server can build a more sophisticated model, each element of which corresponds to a encrypted component. And the central server cannot figure out what these components are. But they can, so this central server can build a integrated or ensembled model and then send that model back to each individual party. And this result has been applied to many scenarios, including by Google, on a scenario where every mobile phone corresponds to one party. And when they want to update the models on the mobile phone, you can use this idea to encrypt a local model, send it up, and integrate with everybody's model, and update the global model, and take it down to the local. Okay, so here are some references on that, and the work are both very recent. Now, vertically, when we partition based on features, this more or less corresponds to a to business scenario. So when two enterprises want to collaborate, they may have some common users, and they may have some uncommon users. And these users may share some features, but most of the features are not shared. And they wish to collaborate without compromising the user identity and key information. And how this is done is through vertical federated learning scenario. So the first thing is to figure out what users are common between them. And there are well-known and secure algorithms to do that. And in doing this, they don't have to reveal what's not common between the two parties. And furthermore, once they figure this out, they can engage in a model building process by exchanging some encrypted gradient information. So they can send public keys to each other. They can then exchange intermediate results that are encrypted based on the public and private key, and then they can compute their own gradient and loss and finally build their model. So when the models are built, each one holds a piece of the model, and a security proof should be able to show that there's no possible data leaks between each other. And when it's time for inference, for testing or application time, the data has to be further encrypted and transmitted among them in order to get the result of each piece of the model in order to compose them together. Okay, so security analysis, again, is needed to show that in such exchange, there's no data leakage at all. Similar work known as federated multitask learning allow multiple parties, as shown on the right, to collectively build a model while sharing some common parts of the model. And people are welcome to see this work by Virginia et al., which is known as federated multitask learning. Now, at the beginning of the talk, I talked about transfer learning, and in the second part, federated learning. But is it possible to integrate them together? And so another way to put this question is, how do we do transfer learning without sharing data? Okay, so I'm party A. This other people is party B. Now, when I want to transfer knowledge between me and this other person, how do we do that without leaking important user information? And in fact, this can be done through some simple steps. Again, it involves encrypting the gradient and loss information, exchanging them between party A and party B, and then finally decrypt it. And in doing this, making sure that they don't add up to leak the information. I won't go into details, but we have a paper recently called Federated Transfer Learning. And these are some of the detailed steps. It really is possible thanks to homomorphic encryption, which allows us to take the encryption down to the element level. Okay, so this is something I skip. And then you can infer for new users, just like in federated, vertical federated learning scenario. And also, you can avoid negative transfer by performing some sandbox analysis. Okay, and improve efficiency. So to summarize, the vertical federated transfer learning allows two parties to collectively build a model by pooling the different information on features and figure out common users. And in the ideal case, you can prove that this is exactly the same as putting the data actually together. So this is known as a lossless property, which you can prove by going through the algorithm. Now, when we talk about security and privacy, we must remember there has been a lot of work. And one of the fundamental work is known as differential privacy. To put it very simply, the idea is to ensure that when one individual changes in the database, the difference between the distribution of the data is not enough for this change to be detected. Okay, so as you can see in the two Gaussian curves here. And in fact, we can combine this with transfer learning by masking the individual models in the source domain sufficiently in order to ensure privacy or differential privacy. And in this case, in a recent work, it's shown that if we just naively apply differential privacy, the performance, machine learning performance drops dramatically in the target domain. But if we use an ensembled model by randomly sampling the source domain data and compose a ensembled model and then transfer that ensembled model, it's much better. And this also, at the same time, ensures differential privacy. And finally, how do we encourage people to join the federation? And this has a lot to do with game theory and multi-agent system. And in this area, I'm new, but I have some colleagues who are expert in this area, and I wish to learn a lot from multi-agent area. So, this chart here shows this motivation very clearly. Suppose we have a data owner who contributes some data in order to join this federation. Now, say when the model is built and the model made some money for the whole federation, the question is, how do we give some benefits back, some proceeds back to this data contributor in order to encourage this party to continue or further contribute even better data along the way? Okay, so this has to do with a mechanism design, designing a good mechanism in order for this whole federation to snowball. Okay, so we have some experiments which take into account the cost of waiting, the cost of joining, and the benefit of joining the federation, and the gain of the whole federation and distribution method. And a recent work titled Mitigating Herding in Hierarchical Cross-Sourcing Networks shows an example of this. And we compared in particular to a few well-known multi-agent game theory, including coalition games, labor union games, and so on, and found this approach does have some additional advantage. Now, have we applied federated learning in our actual work? The answer is yes. We have tried in a anti-money laundering federation in China, where several banks are working together in order to exchange information and to find out who is doing this thing. And federated learning allows the recall to improve by 15% and the audit efficiency to improve by over 50%. And it's also applied to internet banking and risk modeling, risk analysis, as well as insurance area and retailing, online retailing area. And also to some job safety applications, such as when we have multiple work sites, when workers sometimes forget to wear a helmet, and you use a camera to monitor them. And we have not enough data for any of the sites, but when different construction sites pull their data together, the data is sufficient. But but then you have to use federated learning if you don't want to reveal the identity of these people to each other. And this was successfully used in a company in Shenzhen, China. And here are some performance improvements, like the red bar shows how much improvements there are after using the federated learning approach. So we envision, so these successes encourage us, we envision a more fundamental change in dealing with fragmented data, such as building this federation and letting the federated learning framework to take care of the model building. And users then can sign a contract with the federation rather than individual company. And this can sometimes simplify the process. And we realize that in doing this, we have to comply with the government regulation and make sure that everybody agrees to a common standard. So we have been working with IEEE on setting up a guideline and consortium on setting up a federated machine learning consortium. And this has been approved by IEEE under this P36 52.1. And a first meeting is about to take place in February 21st. And people who, and organizations who are interested are most welcome to join us in this effort. And the website is down there. And likewise, as of this week, our research group in VBank just open source a platform for federated learning. And this shorthand is FATE. It's called Federated AI Technology Enabler. And the website is fedai.com. And people are welcome to visit and use this data and software. Okay, so a few days ago, we gave a tutorial on this platform. And the tutorial notes is also available online on this fedai.com. So to summarize, here in this talk, I addressed a big challenge in AI, which is data challenge, data shortage, data fragmentation, and the need to comply with regulation. And here I presented two separate solutions, transfer learning and federated machine learning, and showed how to combine these together, and finally encourage people to come together and work out a socially responsible solution for AI in the long run. Thank you.
Sort of running late, but we can have a couple of questions. There are mics that you can use. Yes.
Hi, thank you for raising these concerns. My question is is homomorphic encryption of practical use yet? Because I thought it required really big encryption keys to work.
Yeah, it's increasingly practical. In fact, the complexity comes down dramatically in some recent works.
So to be particular, what is your cipher expansion rate for the homeomorphic encryption you're using?
Oh, that I have to check with my developers. Sorry. We can talk offline.
In your talk, you mentioned about transfer learning to deal with those domain with less data. But how do you see meta learning stuff in this for solving the kind of problem, like a few shots, zero shot, or something like that?
I think these are all
Does
different.
that involve this topic?
Yeah, it's very related. I think zero shot, a few shot learning, meta learning are all different ways to address specific areas of transfer learning. And in particular, the AutoML tries to automate the process of parameter tuning. And when we deal with cross-domain settings, meta learning comes in, and the automation process is an important part of transfer learning. Yes.
Hi. In the federated learning context, have you looked into malicious actors and whether the mechanism is robust?
That's an excellent question. Yeah. So here, so far, I've assumed that everybody is has goodwill, and but if one of them is malicious, we have to deal with using adversarial learning, and these are yet to be developed, and one of the research topics we are looking at. Yes.
Thank you.
Thanks.
So maybe a second question.
Yes.
Hi. The GDPR also says that you should collect the minimum amount of information to power your application, but I guess with if you want to ensure you don't have fairness issues, you should collect as much data as you can to ensure that you don't discriminate. So I was interested in your take about this. I'm also interested in the take of the whole room about it, so please reply one by one. Okay.
Right. Yes. So fairness issue is important. If you just collect data that are biased and collect a minimal amount, you can easily be trapped into a very biased model and end up with some discriminative, socially discriminative results. That's correct. So I think we haven't tried to put a lot of solid work in this, but my take is that you have to build into your model definition and construction the goal of being fair, and you have to have a objective function. That a part of the objective function should be fairness.
Let's take one last question.
I think my question is related to the previous question, but I have a question about the quality assurance. I think if we have individual to hold their own data, it is a problem that for the quality assurance person to investigate whether this system is satisfy all the persons, it's not investigable. I think this one, if we gather the information from the volunteers, I think our database is biased for those peoples. That's why I think if GDPR or other data protection law is applied, there's still in the bias that those who want to volunteering to share information has more property.
Right.
How do you think about this question?
I think that's always a question. So it's not a 1-0 or black and white question. It's a degree of compliance in this aspect, because you can never have enough data and have 100% recall. So it's a process of keep updating, and I'm not sure what GDPR and the people in defining GDPR understands machine learning, but I think it's important for machine learning people to be part of the team who define the law.
Thank you. Thank you.
Thank you. I think we should stop. Thank you, Qiang, for giving us a peek into how machine learning will become more legal in the changing landscape. So let's thank Qiang for the very insightful talk.